I want to give a second proof of Cayley's theorem. Last time we gave one, and then I want to, if we have time, I want to start the setup for the third proof because that one's a little bit lengthy. We might not be able to easily finish it in one lecture. Okay, so just to recall, the theorem is that the number of labeled n-vertex trees is exactly n to the n minus 2. This fantastic formula here, okay? All right. And so proof number 2, this will be by, we're going to find a recurrence relation for it and then solve it by induction. And similar to the previous proof, we're going to count a more complicated structure that makes this one work out a little bit easier. Okay, so what we're going to do here is first fix a set of k vertices, call it A. And let's, k is at least 1 and at most n. Okay, so we just fix some subset of the n vertices. We'll think of the n vertices as being labeled 1 up to n. That's the standard way of labeling anyway. And then we're going to count, well, let's just say let. So let t sub n k be the number of k component n vertex labeled forests, okay, with each vertex of A in a distinct component. Okay, so you fix A, it's just some arbitrary subset of k vertices, and then tnk, that's the number of n vertex labeled forests where you have k components. And not only that, but the vertices of A are distributed among those k components, so they don't appear in the same component twice. Let me illustrate a simple example here. So there's fewer of these things here than the total number of k component n vertex labeled trees because of this additional restriction that the vertices of A be in different components. So let's say we have like a really simple forest here that has 2 components like this, and then maybe some other stuff, okay? And say A is just the vertices 1, 2, okay? So we might have a labeled tree like this, 1, 7, 6, 2, 4, something like that. And the other labels are somewhere else here. So this is counted by this guy here because this, and suppose there's, okay, actually, this is the whole tree here. Because I said A is 2 elements only. So this is K is 2, so there's 2 components. I don't need additional components. So let me maybe redo the labels here just so that it works. So we'll say 1, 3, 4, 2, 5. Okay, there's one labeling of that forest. The same forest, though, has, of course, other labelings. But for instance, this labeling here, which is one of many, this is not counted by TNK, right? You already see that 1 and 2 are in the same component here, which is not counted by this configuration, all right? So again, TNK is not all of the K component labeled forests. It's only some of them, those special ones for which A is distributed. Now, keep in mind, this quantity here, like the actual number here, only depends on the size of A. What's actually in A doesn't matter, right? If I listed A was 1, 3, then the exact forests that are listed are different, but the quantity of them, of course, is the same because like 2 and 3 are just interchangeable vertices. Like if I enumerated all the ones that satisfied this, the ones that satisfied would be the same here if I just swapped 2 and 3, okay? So the size of A is what's important here. We will use different values in A for different steps of the proof, okay? But the key point here is that observe that if we can count this thing, then all we want to know, we need to know, all we need is Tn1. Because what's Tn1? That's the number of one component, n vertex labeled forests, well, those are trees, right? One component forest is just a tree. And the condition on A here doesn't contribute anything anymore because it just says that A be in a distinct component. But when k equals 1, A is just a single vertex. So we're just asking that vertex 7 be in this one component. It doesn't add anything. So we don't have to like do any weird, divide by n like we did with the root last time. A doesn't contribute anything in this case here. In the other cases, though, it does reduce sort of the space of possibilities. Okay, and somehow that makes the situation easier. Okay, so in order to start doing the proof, so we'll end up getting a formula for Tnk, and then just plug in k equals 1 to get the answer. But we're proving something more general here. Although this object, these k component forests with the a vertices distributed, is like, I don't know why you would care about such an object. There's probably a good reason, but okay. So let's just start off by let f be an arbitrary forest counted by Tnk, with, let's say that a, just to start the example here, happens to be the integers 1 up to k. Okay. Again, I said that the size of a is what matters, not the actual vertices in a. So for this first example, the vertices in a will just be numbers 1 up to k. Okay. So forest is in. So this f, looks like, you've got a component, a component, a component. You've got k components, and the vertices 1 up to k appear in different components. Okay. There's other stuff in here. Potentially, maybe there's a component with a single vertex, and so on and so forth. Okay, so that's my that's a forest that's counted by Tnk, and the goal of this proof is to come up with a recurrence relation that relates Tnk to other values of Tnk, Tn prime k prime, to come up with like a recurrence. Like think of like the Fibonacci recurrence is a really simple one. This is going to give us a pretty complicated one, but that we can actually deal with nicely. So what I want to do is figure out a way that I can build f out of like a different universe of these things here. Like if I start with different forests with more components or fewer components, how can I get to f? Okay. And actually last time we saw something similar to that, where we added these oriented edges, and then that like, squeezed two components together, reduced the number of components. And so here we have a different strategy, but the idea is the same. Okay. So for this one, let's suppose vertex 1 has degree, say d of 1, equal to just I, some I. I don't know what I is. I could be anywhere from 0, right? This could be an isolated vertex in the component, and I could go all the way up to n minus 1 if f is like a huge tree on its own. Okay, it's just the possible degree there. Actually, that's not quite true. Well, I'll see in a moment what degrees are permissible here. Okay, so suppose it's that, and then let's delete vertex 1 from f and observe what kind of result we get. So we have f up here. Here's f minus vertex 1. So the first component here, okay, I'm going to redraw this. So this component here, what happens to that component when I remove the vertex x from it? Vertex 1 from it, right? It had I edges coming out here. What happens when I delete that vertex? I'll draw an arrow down to here.
You split it into d of 1 components.
Yes, exactly, right? Each of these, this vertex disappears, and at each of these endpoints here is contained in its own component now, which may be a single vertex or might have other stuff, but because it's a tree, there's no cycle, and so chopping off this vertex leaves one component for each of these vertices here, okay? So let me maybe like draw this as follows. So here's 1, and I'm deleting it. Here are the edges coming out of it. Now each of these becomes its own component, all right? But also the existing components remain unaffected. Okay, so here's the component with 2 in it. Here's the component with 3 in it. Here's the component with k in it. Okay, so now this has how many components? Well, it had k, and then it gained. I mean, okay, let's draw it this way. This is the easiest way to see it. Here's k minus 1 of the components. How many components are here? Actually, Van just said it. There's as many components here as the degree of 1, right? 1 for each of the vertices, so I there. So f minus 1 has k plus I minus 1 components. I'll write it that way, or I plus k minus 1, whatever you like, right? Okay. The other way to see it is you had k components and you replaced one of them with I, so you got I minus 1 new ones. Okay, so it has that many components, and we can say that A, so then I'm going to call it A prime. The A for this family here is as follows. So what vertices are definitely in different components in this case here? So 2, 3 up to k are still in different components like before. I mean, there may be other choices for a prime in this specific example, but I want to list one here. So 2, 3 up to k. And what else? What else, right? Because now I have more components, so my a prime better be bigger. What kind of union it with here to make this work?
All the neighbors of 1.
Very good, Eric. Yeah, exactly. The neighbors of 1, these vertices here that were at the ends here, these are definitely in distinct components, right? So I can, and it may only be those, right? If these components only have a single vertex, like I'm guaranteed that choice, but maybe nothing else. So let's say a prime is this, okay? So it's the original k vertices minus 1, because 1's not even in the graph anymore, and then n minus x. Okay, so what I'm trying to do here is show that I could reconstruct. So we could construct an f, so of this type, I'm going to say, as follows. So suppose I wanted to create, I mean, f specifically, just for a second, and then I want to make this more general a little in a moment here. So suppose I wanted to choose f directly. How would I do that? Well, I would look at this forest here, the forest with these components and with these components, with this vertex missing. So let me just cross it out in red here, right? This f minus 1 is a very specific forest. It is a forest living in the following universe. So as follows, take a forest counted by, what is this t what here? What this forest here is, what t n k is it counted by? What's n in this case, or what's the number of vertices?
Is it t sub n minus 1 comma k plus I minus 1?
Yes. Everybody get that? There's n minus 1 vertices where this forest here, maybe I'll call this forest f prime here. So f prime has n minus 1 vertices. It doesn't have vertex 1. It's on vertex set 2 up to n, but I mean, that's the same as being on 1 up to n minus 1. It doesn't matter. And how many components are there? Well, we figured out the number of components. There's this many components. And with a being equal to 2 up to k union. Okay, this is a little bit weird to write. Oh, by the way, when I said n of x here, that's n of 1. There's no x, right? So let me erase that. That's it's n of 1. Now up here, n of 1 made like perfect sense, like it was defined. Down here, n of 1 doesn't like make sense because like I'm starting with a tree here. But I mean, this can be any vertices. This is I vertices, right? There's I vertices in this set here, and they're split up. And then what do I do? So that gives me this graph here. This graph here exists in this universe, right? And then I just add 1 to it and join 1 to the vertices that should be its neighbors, right? If I was trying to produce it, okay? So what I'm trying to explain here is that every tree f can be built by looking at the appropriate f prime here. And this f prime is unique. Okay, think about that for a second. But if I have a specific graph f and I remove vertex 1, I get the same forest every single time, the same labeled forest, right? It's not like there are multiple ways to add this single vertex 1 onto this. It has to be joined to the very specific labeled vertices, and these components in here have to be the same as they would be in F, and these components would have to be the same as they would be in F. Okay, so there's only one way to do this. So for each F, there's exactly one F minus 1 that produces it, and that lives in this guy here, at least if F's the vertex 1 has degree I. But there are other trees where vertex 1 has degree different stuff, okay? So let me write down the recurrence we're gonna establish here, and then this actually establishes it, but let's think about it a little bit more after I write this down. So I'm gonna call this a claim, although we've essentially proved it now, but so TNK, so every forest of this type here can be counted by the following sum. So I ranges from 0 up to n minus k. I'll explain that in a moment here. And you have n minus k choose I, and then you have t n minus 1, this quantity up here, k plus I minus 1. Okay, that's my claim. So why is this true? Well, think about how all the different ways we can build up a forest that's in the left-hand side here. Okay, here let's say that A equals, again, 1 up to k, as we've had it before. It could be any fixed set of k vertices, though, okay? So how do we produce a tree of this type? Well, as we saw, trees in this universe here, forests in this universe, have a vertex 1 with degree. The degree could be 0, it could be 1, it could be 2, all the way up to, the degree could be as high as n minus k. Why can the degree be as high as n minus k and not be all the way up to n minus 1? Like normally you could always have a vertex of high degree. Why did I stop here? It has something to do with this set A here.
So when we assume that, by assuming that those are all like different connected components,
yeah,
we assume that they're not, connected with edges.
Exactly, to 1, right? These vertices, 1 up to k, are in distinct components. So there's no edge from 1 to any of these vertices, including 1 itself, right? Because otherwise that would be in the component with 1, violating what's being counted here. So vertex 1 actually has maximum degree n minus k, and it has minimum degree 0, right? It might have no edges going out of it. So this means in order to construct a forest from here, first of all, I say, well, let's choose the degree of 1, because there are definitely forests in this universe here whose vertex 1 has degree 0, has degree 1, has degree 2, has degree all the way up to n minus k. Like we can imagine ones of all those types, okay? So that's the, okay, so I'm going to put this, so first choose degree of 1. That's the first step, okay? And it can be done in I equals 0 up to n minus k. Those are the number of choices. So that's the sum here, okay? Once I've decided the degree of 1, what's this binomial coefficient coming from? That's coming from the actual neighbors of 1. So let me draw again. Here's 1, and say I decided that it has degree 4, right? 4 vertices coming out of it. 4 adjacent vertices. Now, if I look at the label, like this is a part of F, right? These neighbors, there are 4 of them, so it's 4 in this list here. But which 4 they can be? They could be any of the available vertices. So anything other than 1 up to k, right? Those are not adjacent to it, but this could be like 7, 3. Okay, let's say higher numbers, like 101, 25, 16, 9, or something like that, right? That's one possibility for those vertices. These numbers come from the n minus k numbers that are not 1 up to k. And I choose I of them. For a different choice of these numbers here, I will end up with a different, remember, labeled. These are labeled forests. So a different assignment of labels here means a different configuration here, okay? And then, in order to finish this, I have to actually fill in the graph. And how does the rest of the graph go? Well, there's actually a component living here, living here, living here, living here, and then there's the components with 2, with 3, and so on and so forth, right? These other components have to be filled in as well. And how many ways can we do that? Well, that's this here, right? That's the number of ways to build a forest where I have n minus 1 vertices to use, and I have k plus I minus 1 components who contain vertex 1, 3, and so on, and 101, 25, 16, 9, and so on and so forth, okay? So that gives this recurrence, okay? This is a complicated recurrence, but nonetheless, we do get this precise recurrence here, okay? So every forest here can be is counted by this thing, but it's also counted by this thing. There's one way to follow this procedure and build F, okay? If you think about it for a little bit, if you follow this procedure, choose a vertex degree, choose the neighbors, then choose the forest to fill it out. If you do this in 2 different ways, you will never result in the same forest. That doesn't make any sense, right? At one step, you do something different, and the resulting F will be different. So like there's a bijection between these 2 collections here is what I'm saying. So they're equal. Okay. All right. So now using this claim, let's do some nice stuff here. Okay. So first, actually, you know what? Let's do it a little bit differently. Let's set. So this will make this sum work, and you can think about why these ones should be true a little bit. So T00 is going to be 1. This is a common trick and something that we need to work here. T00 is what? This is the graph with 0 vertices and 0 components that's labeled. There's like one of these. Like this is the empty. This is equivalent to like how many empty sets are there? There's like 1 empty set. Like the induction will not work if we don't set this here, but it also does make sense. And then here's where it's a little bit weird, and we have to like make a convention here. How many forests are there with n vertices and 0 components? Like this is nonsense, right? You can't have zero, you're getting one component at least, and as many as n. So there's none of those, okay? So again, that's a convention, but like in terms of what this defines, it is actually 0. And again, it'll make these guys work here, okay? So so of course this is for n greater than or equal to 1, right? I mean, because 0, 0 is 1, and then n0 is 0 there, okay? All right, now we have another claim, which will prove the theorem. And the claim is as follows, that TNK, and we'll be using induction in this claim here. I'm not going to state all the base case and everything, which I hope it'll be evident, but k n to the n minus k minus 1. So that's our claim. So for k equals 1, so again, the number of k component n vertex forests with the vertices distributed as we needed is equal to this nice closed form here. And when k equals 1, this just says that tn1 equals 1 times n to the n minus 2, right? We got what we wanted. So we proved something stronger, but what we at the end we plug in to this guy here, and that's the answer. That's the thing we're trying to prove, right? As we established early on, this extra subscript comma 1 has no bearing on this specific case here. Okay. All right, so how do we prove the claim? And once we prove the claim, the proof, that finishes the theorem. Now that we've got the setup here. Okay, so let's first write out the recurrence that we've established. So TNK equals I ranging from 0 up to n minus k. At this point, there's no more graph theory. This is just symbol manipulation, but there's a few cute tricks, so I thought I'd go through it. But at this point, I would say it's just combinatorics. N minus k choose I, t n minus 1, n minus k minus, let me get this right, n minus, not k, minus I minus 1. Is that right? No. That's the next step. K plus I minus 1. That's what we proved above, right? There's someone nod their head or something if it's right. So okay, thanks Dakota. So okay, so first step, I'm going to rewrite this by doing a change of index in the summation here. Okay, so let me write out the equality and then just tell you what happened. N minus k choose I, t n minus 1, n minus 1 minus I. Okay, and this is index went from I to n minus k minus I. This is a standard trick. Look up here. This sum, I ranges from 0 up to n minus k. What if I perform the sum in reverse and start with I equals n minus k and go down to 0, for instance? What happens? This value here, k plus I minus 1, becomes n minus 1 minus I. And here, the same thing happens. I get what happens in here is I get n minus k minus I, but binomial coefficients operate very nicely, and n minus k choose n minus k minus I is the same as just n minus k choose I. Okay, these are equivalent. Like, what's in disguise here? Like, there's an intermediate step, but it's actually that this is n minus k minus I. Okay, right? If I change I over to this thing instead, and then reverse the sum, then I ranges from this to this, with this guy and with this guy. But this I just replaced with this above because they're equal. Okay, it's a standard trick. It's very frequent to use when you sum binomial coefficients because of this identity here. It really makes things nicer. Okay, so it's not apparent why that helps us yet, but that was the first little operation there. Okay, what's next? Now let's apply induction, maybe. Yeah, let's apply induction. Of course. So now induction. Okay, so what are we doing induction on? And I think is induction on n or k here? It's got to be n. Yeah, it's n. Yeah. So by induction, we have what? I equals 0 up to n minus k. N minus k choose I. And then I'm applying induction to this thing here. Is that right? Yeah. Right? This has a smaller n value. And so what am I asking for? I've got n minus 1 vertices and n minus 1 minus I components. Okay, which is clearly at most n minus 1, right? This value here always has to be at most the value on the right there, but that's still okay. So according to the formula, we have the claim, right? We're proving this by induction, so we can apply this claim here for values smaller than n. When n is smaller, this holds by induction, okay? So since we're induction on n, like you can confirm, actually the base case is essentially here. We'll work out if you check that, but I'm gonna skip the base case. So this can be rewritten as we get k times n to the n minus k minus 1. So let's figure out what that is here, because it's a little bit tricky. We get the leading term is n minus 1 minus I. That's our k, right? Let me just scroll back and forth a little bit here so we get this. So this is this, and then this is this, and then the exponent is this minus 1, okay? So this is n minus 1, and then the exponent is n minus 1 minus n minus 1 minus I. So I'm going to actually erase that so I don't have to rewrite this thing here, but this obviously simplifies. The n's cancel, the 1's cancel. No, wait. Oh, minus 1, right? The minus 1 comes also from the thing. So if I simplify this, actually, let me do this to simplify it. So this simplifies to I minus 1 as the exponent, right? N's cancel, this 1 and this 1 cancel. I do have an extra minus 1 left over in the exponent there. Okay, so now, what's next? Now let's let us factor this out into the front, okay? Let me actually, again, so we don't have to write everything 100 times. I'm gonna factor it out right. No, I can't factor that out. What am I saying? Okay, let me rewrite it. Let me just rewrite the thing and then say what I'm doing. What I wanna do is factor out the n minus 1 from some of the terms here. So let me rewrite it as follows, and then we'll see that it all works out here. I equals 0. I am gonna insist on writing the indices here because there is one step where it matters. N minus k, choose I, and then n minus 1 to the I, and then minus some. I'll explain this if you're not seeing it yet. Why did I do, it's I equals, I'll just leave 0, but n minus k choose I, times I, n minus 1, I minus 1. Okay, what did I do here? I multiplied this whole thing out. Right, if I multiply this middle term out especially, I have an n minus 1 here and a minus 1 here. Right, and so the n minus 1 went with this n minus 1 here and became this term here. That's the collection of all the terms when n minus 1 is multiplied out. And that happens to be an n minus 1 there, so the exponent becomes not I minus 1, but I. And then there's this minus I left over, and that's everything here. Right, so if you take these two things and combine them together, you clearly get the above there. That's just a simplification there, okay? Yeah, notice that this sum here on the right-hand side, the index starts from 0, but what can I actually replace the index with here? I want to index this from 1 instead. Why can't I just magically change it to starting from 1 instead? Can someone tell me that real quick? What's the 0th term in that sum?
0.
Yeah, it's 0, right? There's an I right here being multiplied by everything. So the 0th term is 0, so it doesn't contribute anything. So I can decide that this sum starts from 1 instead of 0. I mean, it's the same thing. And we're going to do a change of index again in a moment. But before we do that, let's look here. This thing here, anybody recognize that guy? You can actually apply the binomial theorem to this. Okay, remember your binomial theorem, a plus b to the q equals the sum from I equals 0 up to q of q choose I, a to the I, sorry, yeah, a to the I, b to the q minus I. Okay, this is binomial theorem. Here I'm going to apply it with not a is n and b is -1. I mean, well, I mean, I'm going to do n. What am I going to do? What am I doing? I'm going to do it. Okay, let me write out what it becomes, and then it becomes n minus 1 plus 1 to the n minus k. That's if you apply the binomial theorem to this guy, what do you get? I ranges from 0 up to n minus k, the exponent. Exponent, choose I, right? So far, so good. And then n minus 1 to the I times 1 to the n minus k minus I. But this 1 here doesn't do anything there. It's just multiplying by 1. Okay? So, and this is of course just n to the n minus k. This is a pretty common thing to do here. Okay, this is a statement of the binomial theorem in disguise, specifically n raised to the n minus k. Okay, the fact that the exponent is in n and the base is in n is irrelevant for the binomial theorem. You can do it with anything you want there. Okay, but I applied it specifically with n minus 1. That's why you get this raised to the I, and plus 1. So like hidden here is a 1 to the n minus k minus I, but it's 1. It doesn't do anything. Okay, so that's that part. Minus, now let's do let's change the index here. So what do I want to do? No, okay, I'm not going to change the index to 0 yet. I'm going to do another tricky substitution here. So let me add another fact. So A choose B can be written out as A over B times A minus 1 choose B minus 1. Okay, this is a well-known, like, you know, this is the chairperson identity, for instance. But you can also solve this by just checking it algebraically. Like if you multiply this guy out, on the bottom, on the top, you're missing an A from the wanted A factorial with this guy, and on the bottom, you're missing a B from the B factorial, that would be this guy. And the other term on the bottom is A minus 1 minus B minus 1, so you still get A minus B factorial on the bottom. So this is a simple fact here, and we're going to apply it to this guy here. Okay, so this thing here can be rewritten as, let me write it just in the space here. N minus k choose I is the same as n minus k over I, n minus k minus 1, I minus 1. Right? That's this term here using that identity. If I replace this thing here with this, then what happens to the I? We have this like nice I left over. So this I will actually cancel with this I. The n minus k doesn't cancel, like that's left over, but that I can pull out front of the summation here. So I'm going to write n minus k, and then sum, still from I equals 1, right? We changed the 0 to 1, but you'll see now in a moment we're going to fix it. N minus k, and then I have n minus k minus 1, I minus 1. And then the I vanished because it canceled this I here. And then I have n minus 1 to the I minus 1. Okay, that's from the substitution there. Substituting there and canceling, I get this guy here. All right, so now I have n to the n minus k minus n minus k times the sum. Okay, now we're going to do another substitution here. Now this sum here, I want to make this sum start from I equals 0 instead. Okay, so I'm changing. So what's happening here? I'm replacing I with I minus 1. Yeah, exactly. So if I start this sum from 0, where does it end? I know these are easy. I'm just doing some sanity checks here. Where does the sum end? What's the end of this index here?
N minus k minus 1?
Yeah, n minus k minus 1, right? Just think about here. I terminates at n minus k. And wait, am I saying the right thing here? Yeah, right. And then in this sum here, I still have n minus k minus 1. That's unaffected by I. What does this I minus 1 become? Yeah, I put this backwards, right? This is this, right? I minus 1 is being replaced with I, rather. I mean, I could put j instead if it's, but this becomes choose I. And then what about this one? N minus 1. What's the exponent here? I as well. Okay, this is just another change of base here. But now, what do we have? So we just still have n to the n minus k, and then minus n minus k. And then what can we do with this thing here? Anybody see what I can do with this? It certainly resembles the one we did over here a moment ago. This is binomial theorem again, but it's a little bit different. Yeah, exactly, Max, binomial theorem. And Max, what's the exponent in this binomial theorem? or anyone. Well, it's not that hard to type out in chat if you see it. So it's this quantity here, n minus k minus 1, n minus k minus 1. And again, it's n minus 1 plus 1, so it's just n raised to the n minus k minus 1. That's equivalent to this thing here, okay? This is out front. All right, now we're almost done. Let me just change over to black here. Because, why are we done here? I mean, it's just simple factorization now, right? N minus k, multiply this out, and I get n minus k, right? This n multiplies the increase of the exponent there, plus k n to the n minus k minus 1. These cancel, voila, right? It's very, very nice, right? It all comes together pretty nicely. Again, the proof of this claim was not really graph theory. Graph theory was just setting up the recurrence, and then this was combinatorics, but I'm quite fond of this argument here. It's pretty subtle, although these are common techniques that if you had, you know, the graduate combinatorics class, you've seen this kind of stuff a number of times. And that ends the proof, right? So what was the strategy here? We made this recurrence, and then we solved it by induction. There's other ways to solve recurrences, of course. And how did we get the recurrence in the first place? It came from making this bijection between this collection of things and this collection of things here, okay? And that relied on this weird trick of adding this a here, but adding this a here made it so it was possible to have a bijection. If I didn't introduce this, like determining the neighbors, then imagine what would happen. I'd grab a random forest from like here, and then I'd say, oh, I want to add 1 to it, right? But like, say one's neighbors weren't nicely distributed. Maybe the desired neighbors of 1, like 2 of them ended up there. Then I can't say, oh, just add them to what its neighbors should be, because that would create a cycle. So I had to make sure that the neighbors of 1 were distributed as I desired. So I had to add this extra weird condition, this a, that things get distributed how I desire them to. But, you know, we could count that, and it gave this nice recurrence at the end here. Okay, so that's the end of that proof. Let me do some of the setup for the next proof that we're going to do next time. And because this stuff's useful anyway, like this will be helpful to us later on in graph theory anyway, but we'll use it specifically for this proof here, okay? All right, so again, in this next proof, we're going to prove something even stronger than we've done, and that's going to come from the following observation. So observe that the number of labeled n-vertex trees is exactly equal to the number of spanning trees of the complete graph Kn with labeled vertices, right? I mean, every single spanning tree of Kn just represents every single tree you could ever have, because Kn has every single edge present. So a spanning tree in it is just a tree. So I mean, like in these problems, at the same time as figuring the number of labeled n-vertex trees, we found the number of spanning trees of Kn, but they're just equivalent, so it's not terribly interesting. However, we can prove a theorem that finds us the number of spanning trees of any connected graph. Like no matter what the connected graph is, we can get the number of spanning trees. That's much stronger. We could apply it specifically to Kn to get our answer, but actually it proves something much, much stronger, okay? So I want to set that up, and this proof does use linear algebra. And so like I said, if you haven't had a linear algebra course, and some of the details of not what we do today, but what we do on Friday will maybe not be clear, but we're going to go through it anyway. I won't be assigning homework or exam questions on this type. Maybe to the grad students, like I said, I might give an easy like linear algebra type question, but to the undergrads, yeah. I assume every grad student has had a linear algebra course. I hope that's true. If not, you just talk to me. We'll figure it out. But okay, so so the goal here is let's find a way to count spanning trees in arbitrary connected G. So not just the complete graph, but any one here. Okay, so in order to do that, we're going to need some linear algebra. And to do some linear algebra, we need like things that you work with in linear algebra. What's the canonical object that we like to work with in linear algebra? There's 2 answers here. I'm looking for one of them, but someone come on, someone tell me 1 or 2 words. So matrices, yes. Okay, good. You guys are, the other one is vector spaces, but we'll deal with matrices. So we want to convert graphs to matrices somehow. And there's 3 ways to do this. There's a most obvious way, which is the one we're not going to use. So okay, so we've got G, and let's whoops, let's put the vertex set of G, let's give it names. So V1, V2, up to Vn. And think of these vertices as being distinguished, right? And E of G, as being labeled. E of G, so the vertices of, the edges of E are just pairs from this guy here, but let's give them individual names. So E1, E2, up to EM. So you can think of these guys as being labeled because they are labeled by the fact that they come from two labeled vertices, but it's not material to the proof here. This is just the names of them, okay? Okay, so the first matrix is the incidence matrix, IG of G is, so so I of G is defined by the individual terms here. So we usually call this guy, actually, I'm just gonna call it is the matrix B, and the individual terms of B are Bij, defined as follows. So Bij, it's a 0, 1 matrix. You have 0 or 1, and you have 0 if Vi is in Ej, and this otherwise. So I should have said this is an N by M matrix. So the size of the vertex set cross the size of the edge set. Okay, this just records incidences. I'll draw a picture of these in a moment. I just want to give the other matrix and do them simultaneously. But the incidence matrix, all it records is the rows are your vertices, the columns are your edges, and there's a 1 in the entry if the corresponding vertex is in the corresponding edge, and there's a 0 otherwise. Okay, so it just records incidences. The Laplacian matrix, L of G, is N by N, so vertex by vertex, so Lij, so the terms have 3 possible outcomes. They can be the degree of vertex I if, what? I is not equal to J? I have no idea what that means now. I'm like super confused looking at my notes. So -1 if Vi, Vj is an edge. I know what and 0 otherwise. This is probably a typo in the written notes. This is.
Yeah, that is a typo. I was gonna
do the notes say not equal?
Yeah.
Yeah, okay. I found a few other typos in that specific one, including the pictures. I already updated. I'll fix this one too. I'll re-upload. It seems I'm re-uploading the notes every week. So, okay, cool. Thanks for that, Cameron. So if they're equal, that's the Laplacian. Okay. So let's look at a specific example again. It's the one in the notes, and work out these two matrices just to help ourselves here. So let's say our graph is this guy here. And then I'll mention one other matrix too that we're not going to use yet, but V1, V2, V3, V4. And then the edges are E1, E2, E3, E4, E5. Okay, so the incidence matrix should be a 4 by 5 matrix, right? And it's indexed here by V1 to V4 and E1 to E5. And we just record a 1 or a 0 if you have the appropriate incidences. So E1 here contains V1 and V2, but no other vertex. So I have a 1 here, and then zeros here and here. Okay. So actually, by the way, can someone tell me immediately how many 1s will be in each column?
2.
2, exactly, right? Each edge contains 2 vertices, so each column will contain 2. And how many 1s will be in a row?
The degree?
Yeah, the degree of the vertex. It'll be how many edges contain that vertex. So this actually records nice information, right? The 2s are obvious, but the rows sums are the degrees of the corresponding vertices. Okay, so let's continue here. So let me actually write E3, E2, E3, E4. Let's make this a little bit easier. So E2 is 0, 1, 1, 0, I think, right? V2 and V3 are in there. E3 is V3 and V4, so 0, 0, 1, 1. E4 is V1 and V4, so 1, 0, 0, 1. And E5 is V4 and V2, so it's 0, 1, 0, 1. Is that right? Did I make a mistake here? I feel like I made a mistake. What I have written in my paper notes here is not what I've established here, but and I don't know what's in the written notes as well, but I think I got it right. E1 has 1 and 2, so this is V2, V3. E2 is V2 and V3, the middle two. E3 is V3 and V4, these two. E4 is V1 and V4, yeah. And E5 is V2, V4. V2, V4. Yeah, seems to be okay, all right? I hope it's clear anyway how to derive this. It's pretty simple. L of G, this is a 4x4 matrix. So it's indexed by V1, V2, V3, V4. V1, V2, V3, V4. Okay. And the one that's drawn in the notes it has a mistake, but for index when I equals J, so the diagonal values, what should I put in the diagonal values according to the definition? Diagonal values are the degree of the corresponding vertex. Okay. So V1 has degree 2, V2 has degree 3, V3 has degree 2, and V4 has degree 3. I think in the notes I'm missing one of these is supposed to, I think this is a 2 and should be a 3 or something like that. I'll fix it. Actually, I'm a little worried now. Did I label this differently in the notes that I'm doing now here? Whatever. I'll fix the notes and upload them. I mean, this hopefully makes things clear. Okay, so then what else do I do? Maybe the second step is easier. So if I have an edge, VI between VI, VJ, I put a -1 and I put a 0 otherwise. Strangely enough, but that's what I put. So V1, V2 are joined by an edge, so I put a -1. V1, V3 are not joined by an edge, so I put a 0. V1, V4 are joined by an edge, so I put a -1. V1, V2, sorry. Oh yeah. I mean, it's obviously it's symmetric around the diagonal, right? Yeah, because edges, there's no orientation to the edges. And then so 0, -1. And then V2, V3 has an edge. And then V4, V2 also has an edge. And then I think V4, V3 has an edge. Okay, something. Yeah, right. I should only have 2 zeros because if you think about this, there's only one edge even missing from this picture here. Like there, so there should only be a pair of zeros there. So that's my Laplacian. There's a relationship between these two matrices. You can get one from the other with the appropriate multiplication, a little fiddling about. There's an exercise for that. Let me mention one more matrix that doesn't come into play here. We won't use it in the proof, but it is important, and that's the adjacency matrix. And in a lot of ways, that's the most natural matrix. The adjacency matrix, and let me just say it in words since we'll define it later. The adjacency matrix is indexed vertices by vertices, and I put a 1 in the corresponding index if the two vertices are joined by an edge, and a 0 otherwise. So basically, I follow the rules of the Laplacian, except I don't put -1s. I put 1s when there's an edge. And the diagonal doesn't have the degree, but it has 0s because vertices are not adjacent to themselves. Unless you allow loops, then you can do things like that. But the adjacency matrix is a very simple object as well. It's also related to, all these three are not interchangeable, but encode the same information in a sense. Okay, good. So that's the Laplacian and the incidence matrix. And let me just end with, what will happen is, in order to find the number of spanning trees, we will prove a theorem that basically taking the determinant of the Laplacian will be the answer. It's not quite the Laplacian, it's a slight modification. And so if we can do that then we have a computational way to figure it out every single time. In practice, figuring out the determinant of like some weird arbitrary matrix is not that easy. But if you think about it, the Laplacian, and we'll do this, of the complete graph is very, very simple. And we can take the determinant of that one and it will spit out n to the n-2. And it's really, really cool. But we need to prove first that it actually gives you the spanning trees, and that is far from clear how to do that. But that's the topic for Friday. Okay, so let's stop there.